Good morning, everyone. We are recording now. So let me know if there is anything that you would like to discuss regarding duality so far. So we made this table here. We filled up some of the entries using weak duality. I want to fill up more entries using strong duality. Okay. So let's just recall what strong duality says. Here is one version. If there is an optimal solution for the primal, then there will also be an optimal solution for the dual. And in particular, the values will be equal. C transpose X bar will be equal to B transpose Y bar using the standard notation. Okay. All right. So let's go here. So which means if one of them is optimal, the other one has to be optimal. So that means that we know that this is always going to be the case using strong duality, and in fact these two can never be the case. Okay, and there is one box remaining. Any guesses what happens here? What do you guys think? Is it possible to have a situation where the primal and dual are both infeasible, or do you think that's not possible? Okay, no guesses?
Seems like it might be possible.
Yeah. Sorry, it might be?
It seems like it might be possible, sir.
It might be possible, right? That is in fact true. So try it yourself. Might appear on one of your assignments. Construct an example. Okay, so in fact the answer is yes, it is indeed possible. Okay, so weak duality, strong duality doesn't tell you anything in this case. You can just construct an example and see that it's possible. Okay, good. So let's continue our discussion about strong duality. So let's go to a new page. I have copied down the same theorem. I also want to state a feasibility version of strong duality, which is an immediate consequence of the other results we are discussing. So this is theorem 4.4. This is generally called strong duality feasibility version. And it says that for a primal dual pair of LPs, if both of them are feasible, then each of them will have an optimal solution and the values will be equal, right? So the assumptions are slightly different. In the previous case, we assumed that one of them is optimal. Now we are assuming that both of them are feasible. Then the conclusion is that each of them has an optimal solution, say X bar, Y bar, respectively. Furthermore, C transpose X bar is equal to B transpose Y bar using the standard notation. Okay. So this is simply a consequence of 4.2 and 4.3. You can check that easily. Implied by 4.2 and 4.3. Okay, so it's all right. So what we are going to do today is we will prove strong duality using the fact that simplex with Bland's rule terminates, which is something we did not prove, right? We will prove it for standard equality form LPs. Okay, so we'll assume simplex terminates, and using that, we will prove strong duality. There are other ways to do it, but that's not the approach we are taking in this offering, right? All right, so let's begin. Okay, so we are proving theorem 4.3. For standard equality form LPs. Right, so let us assume that we have our standard notation, maximize C transpose X subject to AX equals B and X is at least 0. And the dual, we know how to write a general dual now, minimize B transpose Y subject to A transpose Y and C. And because the constraints are equality, this will be free variables. And because this is non-negative, so that is natural, and minimization, the natural will be at least. And so that's our primal and our dual. And what we want to do is, we are going to assume that P has an optimal solution. And our goal is to show that the dual has an optimal solution, say Y bar, such that C transpose X bar is equal to B transpose Y bar. In particular, that means that we need to find a vector Y bar that satisfies two conditions, right? One, we want that A transpose Y bar is at least C, which is the only constraint in the dual. And second, we want what I've already written, C transpose X bar to be equal to B transpose Y. Okay. All right. So we are going to use theorem 2.7, which is that simplex algorithm with Bland's rule terminates. Okay, and I'll just make a note that we did not prove this theorem. All right, and you can imagine what we are going to do is we are going to find this Y bar from our last dictionary. So in the case that you are given a standard equality form linear program that has an optimal solution, if you run the simplex algorithm, you'll go through a bunch of dictionaries. You might use a two-phase method and then come to phase 2, where you will find an optimal solution for the primal linear program. And the last dictionary tells you that you have found an optimal solution to the primal linear program, right? The same dictionary, in some sense, should also tell you the certificate of optimality, which is going to be nothing but an optimal solution to the dual linear program, right? When we were studying simplex, we did not talk about duals, but now that we are here, we will go back to one example after this proof and actually extract the optimal solution for the dual using the last dictionary of the simplex method, or in some sense making use of it. Okay, And that is exactly what the y bar is. It's nothing but a certificate of optimality, right? Notice that these are the conditions for certificate of optimality that we wrote down yesterday. Okay. Good. So by theorem 2.7, simplex terminates. Right? Simplex with Bland's rule terminates. And let x bar denote the optimal solution. Let x bar denote the optimal basic feasible solution found by simplex. Okay. And let B denote the corresponding feasible basis. Okay. All right. So let's recall proposition 2.4 that we proved at some point, right, regarding how to write the given LP in canonical form with respect to a certain basis. Right? All right, so I'll just write down the form. So what we had is maximize y bar transpose B plus C transpose minus y bar transpose A times X, subject to we multiplied both sides by the inverse of the matrix AB, because B is a basis, AB is an invertible matrix. Okay, and X is at least 0, where one of the main things we noticed is that the formula for y bar is given as this. Right, so we discussed this sometime last week. Right, so this basically tells you how to write any LP in canonical form, which I should remind you is equivalent to dictionaries, right? So if you just reorganize things and write it in a certain way, you will get a dictionary. In canonical form with respect to basis B. Okay. So this is going to be our last dictionary, or if you like, our last canonical form LP. And looking at this, we were able to conclude that simplex has terminated and we have a particular optimal solution. Okay. So, all right. So, what does it mean? Consider the last dictionary. Right? With respect to basis B. Okay, so this is what the last dictionary looks like. Right? Use proposition 2.4. So what were the properties of a dictionary or of a canonical form? If you look at this here, all the coefficients were non-negative, non-positive, right? For every coefficient in your last dictionary for the objective function, you had some constant minus a bunch of things, right? In particular, all the coefficients were non-positive. So, by the way simplex works, the coefficients are all non-positive. Okay, and that is exactly what we want here. A transpose y bar is at least C. Okay, so we already have number one property. We now need the next property. We need to somehow show that this holds. Is everybody with me? Are there any questions at this point? So notice that this proposition, its power is that rather than going through the entire simplex method, it directly gives you a formula for any basis. You can write down the canonical form. I mean dictionary, right? All right. So that's good. So it remains to prove that C transpose X bar is equal to B transpose Y bar. Okay, so let's try to do this. So I'll leave some gap here. C transpose X bar. What is that? Well, that is exactly the value of this objective function evaluated at X bar, right? Because this is just the same LP in canonical form. Therefore, the objective function is not really changed. You've just done a bunch of row operations. Right? So it is exactly equal to Y bar transpose B plus C transpose minus Y bar transpose A times X bar. We got this from here. Precisely from here. Okay. All right. So Y bar transpose B is B transpose Y bar plus C transpose minus Y bar transpose A times X bar. Okay. So what we really want to show is we want to show that this quantity is nothing but 0. Okay, and this makes sense. If you think about any of the dictionaries that we had in our simplex method, you see the value of the objective function, whenever you had a specific dictionary, the value was simply the constant you saw in the Z row, which was corresponding to Y bar transpose B. Okay, everything else just evaluated to 0 because of the particular solution we were considering, right? So there are certain special properties about this solution that will make this last quantity to be equal to 0. Okay, and for that we just need to think about what does it mean for a solution to be a basic feasible solution, right? So can someone tell me what does it mean for X bar of n? So remember, we had this notation. You have the basis entries and you have the non-basic entries. So if you look at the non-basic entries, what is that equal to in a basic feasible solution corresponding to basis B? Since X bar is a basic feasible solution with respect to feasible basis B, what can you say about the non-basic entries in your solution?
Zeros.
They are all 0. Exactly. Okay. So what we are going to do is we are going to break this into two parts. We are going to write it as B transpose Y bar plus, what's going on here? You are multiplying a row vector by a column vector, right? So that's going to give you a scalar. So one way to think about it is I will choose specific indices from my vectors and multiply them separately, and then multiply the remaining indices. And that will give you the exact same thing, right? So I'm going to separate the basic and the non-basic entries. Okay. So let's look at C transpose minus Y bar transpose A. Let's see. How do I write this? Let's see. Look at the basic entries of this row vector and multiply it with the basic entries of the column vector x bar. And similarly, consider the non-basic entries separately. Does everybody agree that this is a valid thing to do? Right? Remember, a row vector multiplied by a column vector is simply the sum of the multiplication of the corresponding entries. So I can separate them into two different summations. Right? That's what's going on here. I want you all to be able to see beyond the notation, right? Notation is just to make things easy. So I want you all to be able to imagine what's going on. Okay. Which of these can you conclude is a zero already based on what we have written? Which of these two? Yeah, sorry.
Last one, sir.
The last one, right? Because this is zero, we know that this entire quantity will be zero. So now let's focus on this here. Okay. So what can we say about this? Which of these two components, the left side or the right hand side, one of them is actually zero? Can you tell me which one it is? Think about what happens in a dictionary. The objective function is written entirely in terms of the non-basic variables. And all the basic variables are also written in terms of the non-basic variables. In particular, in the objective function, all the basic entries should be, all the coefficients of the basic variables should be
zeros, right?
They should all be zeros, right? The entire objective function is written in terms of the non-basic variables, right? So this whole thing also should be zero. Okay, so this is a row vector of zeros. Okay, so since this is a row vector of zeros, you also have that. So this is also okay. So you're just multiplying zeros with a bunch of numbers and adding them up. And so therefore, this is exactly equal to B transpose Y bar. Okay. So you indeed have C transpose X bar equals B transpose Y bar, and that is your proof. Okay. Are there any questions or concerns? I want to also do an example. I think we have enough time to do one example and actually find the certificate of optimality by doing the computations we just did in the general case. Right? Okay. All right, so let's go back to the two-phase method. I want to take the example we did then. So I just quickly show it to you. All right, we are already at two-phase. So if you recall, we solved this linear program. First, we multiplied the first constraint by -1 to make the right-hand side non-negative. And then we wrote down the auxiliary LP. We solved the auxiliary LP blah, 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 blah. We got the auxiliary LP to have optimal value 0, which means that the original LP is feasible, and we found a feasible basis 1, 3 for the original LP, and we solved the original LP, and finally we got the basis 2, 3 and the corresponding dictionary. Okay, so I want to look at this example and do everything we did in the general case on this example. Okay, so let's go back to our page. All right, so recall from Two Phase Simplex. Okay, so I'll quickly write down what the LP was. Maximize 2 minus 1, 2, x, subject to minus 1, minus 2, 1, 1, minus 1, 1, x equals minus 1, 3, and x is non-negative. This was our original LP, P, and okay, oops, sorry. I think I pasted it wrong. Okay, fine, doesn't matter. All right, so let's call this our T prime. So what we did is we multiplied the first constraint by minus 1. Okay, so we get a 1, 2, minus 1, and here we've got a 1. Okay, we found a feasible basis for this one, and the feasible basis was 1, 3. This was found by phase 1 of the two-phase method. Right? And then we wrote down the auxiliary LP. And we solved this LPP prime starting from this feasible basis, and then we found optimal solution by looking at the following dictionary. So the dictionary, the last dictionary was 10 minus 2x1, x2 is equal to 4 minus 2x1, and x3 is equal to 7 minus 3x1. So the basis corresponding to this dictionary is 2, 3, and the solution is 0, 4, 7. Okay, so that's our optimal, that's one of the optimal solutions, the one that we found by Simplex. Right? And what is its value? Its value is exactly what you expect. It is basically the scalar that you see here. Yeah. Okay. So what we want to do is we want to find the corresponding y bar as we did in our proof of the strong duality theorem, right? Which is also, not only is it an optimal solution to the dual LP, it is also your certificate of optimality along with x bar. Okay. So what we are going to do is we are going to apply proposition 2.4 and compute y bar as AB inverse transpose CB, where B is going to be our optimal basis 2, 3 that we found at the end, right? So we compute y bar using proposition 2.4. So y bar is going to be our AB inverse transpose CB. So let's look at AB. So we are looking at the second and third columns of our matrix. So it's 2, minus 1, minus 1, 1. Take the inverse and the transpose. multiplied by CB. CB is the second and third entries of the cost function or the objective function. Minus 1, 2. Okay. And if you take the inverse and do the transpose, turns out what you get is the following. Okay. And let's do the math. So first row times first column is minus 1 plus 2 minus is 1, and minus 1 plus 4 is 3. Right? So this is for P prime. Notice that when we solved the linear program, we were actually solving P prime. Of course, P prime was just obtained from P by multiplying the first constraint by minus 1. Right? And so we are just going to multiply the first entry by minus 1. Right? That's all we have to do. So for P, we have minus 1, 3. Okay. Good. So let's check. Let's check if minus 1, 3. I should mention that this is the same coincidence that happened earlier. Minus 1, 3 is also the vector you see here, which is a complete coincidence. Okay. So please don't pay attention to that coincidence. All right. So let's check that minus 1, 3 actually satisfies the things. Right. So let's check that y bar is indeed an optimal solution for the dual LP, and x bar y bar is thus a certificate of optimality. Okay, so let's write down the dual of this LP. All right, so it's not difficult, is it? It's minimize B transpose Y. So our B is minus 1, 3, subject to A transpose. So that's going to be, well, I've written it down in my notes. So I'm just going to copy it down quickly. Minus 1, 1, minus 2, minus 1, and 1, 1. Okay. Y is at least C transpose, and that will be 2 minus 1, 2. Let's check. 2 minus 1, 2 was our objective function in the original language. And Y's are free variables. Okay. So let's check that what we have here, Y bar, is an optimal solution for the loop. So in particular, the first thing is to check what is A transpose Y bar. So it's and Y bar is minus 1, 3. Okay, so it's 1 plus 3, 4, 2 minus 3 minus 1, and minus 1 plus 3, 2. And is this greater than equal to 2 minus 1, 2 entry wise? It is indeed. Okay, so it is a feasible solution for the dual. And the second point is whether C transpose X bar is equal to B transpose Y bar. Right. So let's see what B transpose Y bar is. So it's minus 1, 3. Yeah, so this is where the coincidence happens. That's the same vector really. And so that's 1 plus 9 equal to 10, which is exactly what we expect because the value of our optimal solution is indeed 10, right? So we Let's just make sure C transpose X bar. So what is our C transpose? It's 2 minus 1, 2. And what is the X bar we found from? It's 047, right? By looking at the last dictionary. So you have 0 minus 4 plus 14, which is 10. All right. So the point I want to make is that it gives us a procedure for finding the certificate of optimality from the last dictionaries, right? So the last dictionary, not only does it give you an optimal solution to the original LP, it also tells you how to get an optimal solution to the dual LP, therefore proving that both of these are optimal solutions to the respective LPs. Right? So an optimal solution to the dual from the last dictionary. And our X bar, Y bar will thus be the certificate of optimality for not just the original LP, but also for the dual LP. Okay. So are there any questions or concerns regarding strong duality, right? So is the proof clear? And we also ran the proof on an example to illustrate how the certificate of optimality is extracted using the Simplex last dictionary and this proposition 2.4 that we proved earlier. All right. So I think more or less that is all I have for today. Right, so we have proved weak duality. Again, all the proofs we focused on SEF LPs. Weak duality is actually quite easy to prove for different types of LPs using the same arguments. I hope you have already tried one yourself. Strong duality, if you prove it for SEF LPs, you can also prove it for all LPs by converting into SEF and then relying on that, right? So there are no new mathematical insights when you try to prove weak duality or strong duality for arbitrary LPs, right? The main insights are already there in the standard equality form version, which is why I don't want to sort of waste time on proving them in the general sense, because there are really no mathematical insights. It's just a matter of bookkeeping. Because you have different kinds of variables, you have to deal with them differently. But the main ideas are still going to be the same. A certain vector will be all zeros, and therefore the product with another vector will be just zero, right? Stuff like that. So that's why, as far as the proofs are concerned, we are focusing on specific types of LPs. And in particular, we are focusing as far as possible on standard equality formulas. All right, so what's coming up next? I think it's going to be a short lecture today. So next, we are going to continue our discussion on duality and going to go slightly deeper into duality and look at a condition called complementary slackness, which you might have seen in some of your previous courses. I'm not sure if you have seen proofs of them, but we are actually going to prove things. Right? So what's coming up next is this really cool thing called complementary slackness conditions, abbreviated to CS conditions. So, and it's related to one of your assignment problems actually. I actually already gave you a sort of peek into it in assignment 1, problem 5. Okay. Although in that case we use counting arguments, but now we are going to use linear programming duality in order to derive the same kinds of results. Okay, so and one more thing I want to discuss is the sort of geometric viewpoint of optimality. Yeah. Okay, so this is also related to the complementary slackness conditions. So that's what we are going to do next, and we will start this tomorrow. And the complementary slackness conditions in particular, as well as duality in general, are going to be very useful in the next module, where we are going to design primal-dual algorithms for combinatorial optimization problems. So let me just make a note here. This is extremely useful in module 5, primal-dual algorithms. In fact, largely the correctness of our algorithms will follow from complementary slackness conditions. Okay. So just to give you a brief idea, it's basically you are given a feasible solution to the primal and a feasible solution to the dual, and complementary slackness conditions will allow you to conclude that they are both optimal solutions by looking at certain specific conditions satisfied by them. So it will be an if and only if thing, right? I think if you think about your assignment 1 problem 5, that is something you did. What you did is you had your shortest path, you were given a certain path, and you were given labels for each ST cut. And you proved that the cost of the path is exactly equal to the sum of the labels, which is like primal solution value is equal to the dual solution value if and only if certain specific conditions hold. And in the next module, we will see that you can solve the same problem using complementary slackness conditions rather than doing counting arguments. Okay. Anyways, so that's just a peek into what's going to happen. And I think that's all I have for today. So we'll continue tomorrow at 9 a.m. I'm here for another 10 minutes if there are any questions or concerns. Okay, I'm going to stop recording now.